opposite was true. If the metric went to 0, the last shape you had must have been a sphere. Here's how we use this to solve the Poincare. Take a random manifold and give it an arbitrary metric g, and see how it changes with Ricci flow. If you can prove the metric will go to 0 in finite time, that means the last shape you had must have been a sphere. But changing the metric doesn't change the underlying manifold. So if you ended up with a sphere, you must have started with something homeomorphic to a sphere. This argument is beautiful, but it hits a snag. You see, in higher dimensions, you can have situations like this, where a point in this neck gets squished to nothing even before the manifold becomes a sphere. This is a problem. If Ricci flow deletes parts of your manifold, you're changing the underlying set. It's game over. Another singularity you might see, a neck with a cap. A Ricci flow could stretch this out and squeeze this point into nothingness. You could also have more complicated snags like the Bryant soliton, where some of the points in the manifold mysteriously vanish. To deal with these singularities, Perelman came up with a strategy. Perelman decided to manually remove the problem areas of the manifold. He then glued pieces of spheres to cover the holes that he had made. Here's how we used it to prove the Poincare. Play out your Ricci flow with surgery and prove that it'll go extinct. Now hit the rewind button. First, you'll see the creation of spheres. Then, you'll see the creation of necks. At each time, you only see the creation of spheres and necks. But two spheres connected by a neck is just a sphere. So at each time, the manifold is a collection of spheres. But the manifold we started off with was connected, so it must have been a sphere. Say what you want, but this argument is just beautiful.